everyone. Welcome. Thanks for coming out for the Astra Space Day. We have here today with us Dr. Bharat Ratra from Space State, and he's going to be telling us about the biggest things in the universe. So, why don't you take it away?
Thank you. Is my mic working? Can you hear me? That's great. So I'm
hard of hearing, so speak loud.
okay. Can you hear me now?
That's perfect.
Okay. And maybe I'll be able to do that for the next 5 minutes, and then I'll lose my voice. So but before I start, I mean, there are these cards that I handed out to you, and it's connected to a really nice website that has really nice videos that clearly explain global warming. The URL is on them. And you're welcome to keep those cards with you. So I'm a cosmologist, and that means I'm interested in the universe and stuff on very, very, very large length scales, and how that stuff changes in time, how it evolves. So I'm going to talk maybe for about 25 or 30 minutes, and then we'll have time for questions. And what I'm going to do is kind of describe how stuff is distributed in the universe, and the distribution is very different when you look at it on small scales compared to what it is on very large length scales. So I'm going to go through that, and then I'll talk a little bit about the various forces that are important. So one's gravity, and that's just stuff pulls itself together if you don't support it, and that was what was kind of quantified by Newton and then improved upon by Einstein. And the other force that's really important for this discussion is the electric force. And we'll talk a little bit about that. And we'll see how we get the expansion from gravity, and that expansion doesn't make us also expand. So we're going to talk about very large length scales. And I'll just start over here. So I've got length scales up here, and this is the size of a typical human. The units I'm using are meters. So 1 meter is about 3 1/3 foot. And a typical human's probably about 1.5 meters or 2 meters. And this is not a linear scale. Each little tick here is a factor of 100,000, either bigger or smaller. And there's a lot going on very, very large scales, and a lot going on in very, very small scales. But we can kind of start out on typical human scales, and we can figure out what parts of reality we can directly access through our senses. So if you're really patient and you've been around long enough, maybe you've walked 1,000 miles in your life, and that's probably 1,500, 1,600 kilometers. So it's somewhere over here, 10 to the 5 or 10 to the 6 meters. So you can't get much further than that. I mean, you're not going to be able to walk to the moon. You kind of have an upper limit, and that's probably like 10 to the 6 meters or so that you can directly access through your senses. And if you have really sensitive fingers and you hold a strand of hair between two of your fingers, or your thumb and your finger, that's probably the thinnest thing you can feel. And depending on how thick your hair is, it's somewhere in over here, 10 to the -4 or 10 to the -3.5 meters. So the scales we can directly access through our senses are in this range here, and it's a pretty small fraction. There's many, many things going on smaller scales and on larger scales. And the physics that describes what's going on over here is called Newtonian physics, because Newton was the most famous physicist who developed this part of physics. And if you kind of think about it, a toddler is a Newtonian physicist. A toddler spends the first couple of years of his or her life trying to figure out how to walk and trying to figure out how to move. And if that toddler doesn't succeed, then the toddler can't do anything. And so every toddler becomes an expert in Newtonian physics. Unfortunately, by the time they get to college, they've forgotten that, and they have to start over again. But you can, if you have a pendulum, you can construct a pendulum pretty easily from a piece of wood and support it at one point. And a way to measure distances, then you can watch falling apples and figure out Newton's inverse square law of gravity. That's all you need. You probably get a pretty approximate relation, but it's pretty good for practical purposes. You can collide balls, and again, if you have a pendulum and a way to measure time from that pendulum and a way to measure distances, you can figure out conservation of energy and conservation of momentum. And it doesn't require a lot of special equipment. But if you want to think about figuring out what a star does, you've got to do something very different. You can't go over there and touch it with your hands and try to figure out the physics of a star. What you're going to do is you're going to take a telescope, collect light from that star. Maybe you'll put a prism in the path of that light and break it up into its spectrum and have a camera there and store it on a CCD, get it on a CCD and store it in your computer. And then you'll go build a mathematical model. You'll put a bunch of atoms and molecules into a big sphere and turn on rotation and turn on gravity and turn on heat and try to get that to radiate and see if your mathematical model would produce those spectra that you're observing. And if they do, then you try to build a more sophisticated mathematical model and try to build better, bigger telescopes and better CCDs and try to capture more data and improve your model that way, the model of the star. And the same thing's true at this end. You're not going to be able to touch an atom or a nucleus or electrons. You've got to build mathematical models and use particle colliders and collect the light that comes off from those collisions or whatever else comes off and then improve your mathematical model. So the way you build intuition over here and over here is fundamentally different than the way you build intuition on human scales. And that's probably the cause of this feeling of a lot of people who haven't taken a lot of physics classes that quantum mechanics and relativity, which govern physics on these scales, are unintuitive or not understandable in the same way that Newtonian physics is. And that's kind of a really important thing to remember, that you cannot use the intuition you develop over here to apply over here and apply over here. You've got to build the mathematical models and make comparisons between the predictions of those models and the measurements you're making through your telescope or through your particle accelerator, your microscope. And that's the way you build up intuition. So a lot of people aren't really familiar with how big this range of scales is. So I'm going to spend a little bit of time walking out that way. And there are two really nice videos. I guess there are no writing implements here. One's called The Powers of 10. I think both are called The Powers of 10. And one is by the Eames brothers. That's E-A-M-E-S. They were architects, and that's from, I guess, the 1970s. And you can probably find it on your favorite search engine. And the American Museum of Natural History has an updated version of that. And it's well worth looking at these videos when you have time. They're only probably about 15 minutes long. And they kind of go and look at much larger scales and much smaller scales. So today I'm just going to focus on larger scales. So we're going to look at a typical human scale. And some of you probably recognize this person. And we're going to use a new system of units. So we're going to measure lengths in terms of Einsteins. And an Einstein is roughly 2 meters, or about 6.5 feet. And we want to get some idea of this picture, this planet, which is Earth. And a picture like this has become possible only in the last 60 or so years when we've had satellites in space with cameras. And we want to compare this to this guy. And so what we're going to do is take a drilling rig, put it at the North Pole, and drill a hole all the way to the South Pole and build a huge, strong base there. And then we'll go and get 6.5 million Einsteins, and we'll place the first one on that base, and the next one on his shoulders, and the next one on his shoulders, and so on. And if you have 6.5 million Einsteins, you'll cover the diameter of the Earth. And 6.5 is roughly 10, so we can say 10 million, which in scientific notation is 10 to the 7. So you're going a factor of 10 million from a human scale to the scale of this small planet. Then we can keep going and look at this object, which is our sun, and try to do the same sort of thing. And maybe it's easier to do this in terms of Earths. So if you pile Earths one on top of another for a factor of 100 Earths, you'll cover the diameter of the sun. So the sun is 100 times bigger than the Earth. And if you want to do that in terms of Einsteins, it's about 750 million Einsteins. We can go another step, and this is the solar system. And we can focus right over here first. So the Earth orbits the sun, and that distance from the sun to the Earth in meters is 1.5 into 10 to the 11 meters. And that's bringing you many, many, many powers of 10, which is very, very inconvenient. So the way to think about this is to think about how many suns you need to put in a row to get from the surface of the sun to the Earth's orbit around the sun. And it's another factor of 100. If you pile 100 suns in a row, then you'll reach out to the Earth's orbit. So you go a factor of 10 million from a human scale to the size of the Earth, and another factor of 100 from the Earth to the sun, another factor of 100 from the sun to the Earth's orbit around the sun. And so because there's so many meters in that length, astronomers prefer to use different length units. And one unit they use is called the astronomical unit, or the AU. And that's basically the Earth's radius, the Earth's orbit radius, when you average it out over the course of a year. So you can average it out and it becomes a circle. Otherwise, it's slightly squashed. And so sometimes the Earth's a little bit further away from the sun, and other times it's a little bit closer to the sun on average. And if you average that out over the course of the year, that radius is called the AU. And in terms of meters, it's that. And that's a good unit to use when you're studying planetary systems. But there's also another unit you can use, and that's how long it takes light to travel that distance. So light is very, very unique. It's perfected cruise control. When light goes in vacuum, it always travels at exactly the same speed, no matter what direction it's moving in. And that's a very, very big speed. In terms of meters per second, it's 3 times 10 to the 8 meters per second. And here, it might be a little bit useful to think about it in terms of feet per second. So a meter is 3 1/3 feet. And if you take this 3 and multiply that by 3 1/3, when we replace the meter by 3 1/3, you get about 10. And so it's 10 times 10 to the 8, which is 10 to the 9. So it's 1 billion feet a second. So light is very, very fast, and it covers 1 billion feet in a second. Or if you think how long it takes to cover a foot, which is this distance, it takes roughly a nanosecond to cover that distance. So it's going really, really fast. And because it's going really fast, you can divide this distance by this huge speed, and you get 500 seconds. So the distance between the Earth and the sun is covered by light in 500 seconds. So when you look at the sun, and if you're going to look at the sun, you should be really careful and use protective equipment, otherwise you're going to damage your eyes, your retinas. But when you look at the sun, you're not looking at the sun at the present. You're looking at the sun 500 seconds ago in the past, because that light that's hitting your retina now started traveling towards you from the photosphere of the sun 500 seconds ago. And this is true of anything you look at. And if you look at your neighbor's probably about 2.5 feet away from you. And it takes light 2.5 nanoseconds to get to you from your neighbor. So you're not looking at your neighbor in the present, you're seeing your neighbor 2.5 nanoseconds in the past. And your brain doesn't care about nanoseconds. It's not sensitive to such small times. And so it automatically assumes you're seeing that person in the present, and it allows you to carry on a conversation and stuff like that. But you're always seeing things in the past. You never see anything in the present. And this is kind of important when you get out to really, really large distances. So it's 500 seconds to get to the sun at the speed of light. So we can go look at the next nearest star to us, the nearest star to the sun, and that's Proxima Centauri. And that's about 100,000 times further away from us than the sun is. And it takes light 4 years to travel from Proxima Centauri to us. And if we turn that distance into AUs, it's 200,000 AUs. So when you're looking at stars that are distributed in space, the AU is also not that good a length unit because you need too many of them and you carry around many powers of 10. So astronomers introduce a new length unit, and that length unit is described in this cartoon over here. It's called a parsec, and that is an abbreviation for a parallax of an arc second. And it's also abbreviated down to a PC. So that stands for a parsec. And the way this unit is defined is you take your favorite astronomer and you give her a telescope and a protractor to measure angles, and you've got to be able to measure really, really small angles. And you send her off away from the solar system, and you send her off so far that this huge distance, this huge linear distance of 1 AU, subtends an extremely tiny angle at her, an angle of 1 arc second. So if you go around a whole circle at 360 degrees, and you can break each degree up into 60 arc minutes, and you can break each arc minute up into 60 arc seconds. So if you multiply 360 by 60 by 60, you have roughly 200,000 arc seconds in a whole circle. It's a really, really tiny angle. So if you want this huge distance to subtend a really tiny angle at her, you have to send her away pretty far. And when it does subtend 1 arc second at her, then she's 1 parsec away. And in terms of light travel time, it takes light about 3¼ years to travel a parsec. So if you send light out somewhere and wait for 3¼ years, it'll have traveled a parsec. So we can change from AUs to parsecs, and Proxima Centauri is roughly 1¼ parsecs away from us. And that's the nearest star. We can walk out further and look at this guy. This is where we live. It's our Milky Way. It's our galaxy. How many of you have seen the Milky Way? That's great. So those of you who haven't should try to see it. And there's observing nights at the observatory here. And there's also another amateur astronomy group in Topeka called NECAL, NEKAAL. So you can find them on the web, and they have telescopes and they have observing nights too. And it's worth looking through telescopes. So this is pretty much like a frisbee, except it's got a little bulge in the center. So it's a disk. And if you look at it from the top of the bottom and you look at the frisbee head on, you'll see the spiral arms of the Milky Way. But when you're looking at it from the edge, you don't see those spiral arms. So it's got a bulge in the center, and it's a disk. And maybe we can start out with the diameter of the disk of the frisbee. So it's up here in numbers. It's 50 kiloparsecs. Kilo is 1,000, so it's 50,000 parsecs. And I told you 1 parsec is about 3¼ years of light travel time. So if you multiply 50,000 by 3¼ you get about 160,000 years. So if you started something out here that could travel at the speed of light, and it can't be us, it's got to be massless, and you point it in this direction, it'll take 160,000 years to cover this distance. And that's pretty huge. So the distance between Earth and the Sun is 500 seconds. The distance between Earth and Proxima Centauri is 4 years, and this is 160,000 years. So it's a collection, it's a huge collection of stars, maybe 150 billion to 200 billion. And the typical star is probably half as massive as the sun. So the sun is not that atypical a star. So it takes 160,000 years to cover this. The sun is about 1/3 of the way out from the center. This region is called the central bulge. And right at the center, we have the galactic nucleus. And that's where our big black hole lives. It's about 4 million times as massive as the sun. And that seems like a huge number, but it's actually pretty puny on the scale of black holes at the centers of galaxies, which easily get up to 1 billion times the mass of the sun. So this guy is embedded in something called a halo. And this halo is about 10 times bigger, so maybe about 1.5 million years in light travel time. And it's much darker than the shiny part of the galaxy. And it's where a lot of dark matter lives. And in this halo, there are these things called globular clusters, which are the oldest stars. These are collections of the oldest stars known to us. Some of these stars are 12 or 13 billion years old, and the universe is only about 13.75 billion years old. So they're almost there from the beginning of time, pretty much, at least for the Big Bang model. What happens before that is not completely clear. So these guys are bound together, and they're collections of hundreds of thousands to maybe 250,000 stars, and they orbit the disk of the galaxy in 3 dimensions. So they just kind of go around. And they're pretty beautiful to look at through a telescope. Has anybody seen a globular cluster through a telescope? I mean, you should try that sometime. They're really beautiful. They're like these little balls of light, and you can resolve the stars in them. So we can go look at our nearest neighbor galaxy, nearest neighbor big galaxy, which is the Andromeda galaxy. And this is another thing you can see in the night sky if you know where to look, and you can see it with your naked eye. It's pretty dim, but you can see it if you know what you're looking at. And it's a spiral galaxy. You can see its bright spiral arms. And it's a little bigger than the Milky Way. It's 60,000 parsecs, so maybe about 200,000 years for light to cross the diameter of Andromeda. And it's about 750,000 parsecs from us. So in terms of light travel time, that's 2.5 million years. So again, the distance between the Earth and Sun is 500 seconds. The size of the disk of the Milky Way is 160,000 years, and this is 2.5 million years for light to get to us. So if you're looking at Andromeda and you're seeing it right now, that light left 2.5 million years ago and traveled in a straight line from a star in Andromeda to hit your retina now. And it's been traveling for 2.5 million years. And that's kind of an interesting time. If we go back and look at what was happening with human evolution 2.5 million years ago, you have to go back maybe a little bit further, and you come across the most famous fossil, Lucy. So do you guys, how many of you are aware of Lucy? That's great. So she lived in Ethiopia, and they've managed to date her to 3.18 million years ago. And apparently there's enough information on her injuries to know that she apparently had climbed up into a tree to get away from predators and to sleep there. And she fell out of that tree, and that's kind of the hypothesis right now. And there's some pretty good evidence suggesting that she fell out of that tree 3.18 million years ago. About 700,000 years before the light you're seeing now left Andromeda, so it's not that much further away in time in the past. So that's Andromeda, and galaxies are pretty heavy. They're collections of hundreds of billions of stars, and stars are pretty heavy, so when they come together, they're going to start pulling on each other through Newton's inverse square law, and they start orbiting each other, and they form what are known as clusters of galaxies. And this guy is a nearby cluster. It's just the center of it. It's the nearby Virgo cluster. And you're probably seeing about 1,500 or so, maybe 2,000 galaxies. Every single spot of light you see here is a galaxy. Some of these are closer to us in the foreground, and the others are further away in the background. And the scale here is a few million parsecs, a few megaparsecs. Or in terms of light travel time, maybe 6 or 7 million years for light to cross this if you let it go and point it directly across at that distance. So this is a pretty huge object, but it's pretty insignificant on the scale of the universe. And this is a bigger chunk of the sky, so I can show you how this picture was taken. So we live 1/3 of the way out around the sun, and they pointed their telescopes up here, and they took a picture of the cap up here, so it's got a certain width. And they recorded this on glass plates. So these are the guys who did it, Shane and Virtanen, and they did this at the Lick Observatory, which is in the hills outside of San Jose in the San Francisco Bay Area. And they took these images in the 1950s and 1960s when they didn't have CCDs. So they would take their big glass plates, put emulsion on it, and stick it at the focus. And they didn't have laser scanners, they didn't have computers, so they sat there with little traveling telescopes. So they have an eyepiece and they hook it onto the two ends of the glass plate and then moved it along. And with paper and pencil, they figured out the positions on the sky of 400,000 galaxies. So those of you who are upset about your homework sometimes can think about this, where they sat there with paper and pencil and figured out the positions of 400,000 galaxies. And this map was made later, but it's a pretty small chunk of the sky, but it's much, much bigger than that cluster I showed you. Here's another famous cluster. It's the Coma cluster. It's about 120 megaparsecs away from us, and it has 5,000 or 6,000 galaxies in it. And it's just a few pixels on this image. There are other clusters in the foreground, so they are bigger. And there are other clusters here, other clusters here. And if you look at this carefully, you can see that there's other structures beside clusters. You can kind of see one-dimensional filamentary structures. And you can also see darker regions. These darker regions are called voids. And the one-dimensional filamentary structures are called filaments. And then there are the clusters. And so the easy way to think about this is to think about bubbles in your bathtub when you're having a bath. And the galaxies tend to avoid the center of the bubbles, the bright galaxies. They tend to hang out on the surface of the bubbles. And where two galaxy bubbles come together, because you're looking at this in projection, you're looking at a brighter one-dimensional structure that stands out because there's more bright galaxies there, and those are the filaments. And where a bunch of bubbles come together with a lot of filaments, they sort of drain into the cluster. So you can see a filament here, and a filament here, and a filament here, and you get the bright cluster there. So this distribution has a name. It's anisotropic. And maybe we should first understand what isotropic means. That's spelled I-S-O-T-R-O-P-I-C. And so if you're standing at one point and you look around you and above you and below you and in front of you and behind you, and if it all looks the same, then you say the distribution is isotropic. So you can do that in this room. If you look above you and look to your left, you don't see the same person. So this room is pretty anisotropic. You could go up 50 miles and look around, and you'd probably be able to see the Rockies to the west, but you might not be high enough to see the Atlantic to the east, but you can tell pretty much that the surface of the Earth is pretty anisotropic. Our Milky Way is pretty anisotropic. Even our solar system is pretty anisotropic. So if you go, and look let me see. So I guess I don't have a picture of the solar system, but if you look at the Milky Way and you look towards the center, then there's many, many more stars there. If you look that way, there's many fewer stars. And even on these scales of that we're looking at here, which I didn't tell you, it's 300 megaparsecs across here. If you multiply that by 3.25, it's about 1 billion years or 1 billion light years for light to cross that. So even on scales of hundreds of millions of years, the distribution is anisotropic. It looks different in different directions. And maybe that's okay because everything else below that is anisotropic. But when you get out further by another factor of 50 or so, the distribution becomes isotropic. And this is what we see. This is the largest scale distribution. And there's a lot of jargon up here. So it says Planck. And this is a picture taken by the Planck satellite, which is launched by the European Space Agency. And it's a picture of the afterglow of the Big Bang. And that's what these words say. It's the cosmic microwave background radiation anisotropy. So it's cosmic. It's on really large scales. It's microwaves. Those are the same parts of the electromagnetic spectrum you use to cook at home in your microwave oven. It's also the same part of the electromagnetic spectrum that police officers use to give you a speeding ticket. So how many people have got speeding tickets? Okay, 2 hands. So what they're doing is they have a microwave source and they're sending out microwaves directionally, pointing them at your car. Those guys get reflected and they have a microwave detector. And they're measuring the pitch of the outgoing microwaves and the incoming microwaves. And from that difference, they can tell how fast you're moving relative to the police officer's car. And you're all familiar with this effect. It's called the Doppler effect. And if you ever stood on the side of the road and a fire engine has gone by you with the siren on, as it comes towards you, the pitch is higher. As it goes past you, the pitch is lower. And that's the Doppler effect. And because the pitch is inversely proportional to the length, the wavelength of the radiation, so the light is an oscillatory wave. It's like somewhat similar to a water wave, and it's got a wavelength. And because the pitch is higher as it's coming towards you, the wavelength is smaller, and the pitch is lower, so the wavelength is larger as it leaves you. And because red light has longer wavelength, people say it's red shifting when it's leaving you, when it's moving away from you, and it's blue shifting when it's coming towards you. And what they have here is a microwave detector and a spectrum, a thing that can generate a spectrum from that, can break it up into its colors. And once you know the color of the radiation, you can tell how hot or how cold it is. And so they looked out on the surface inside the sky, the whole sky, and it's like the inside of a beach ball. You're measuring the light that comes to you from that surface, and you're sitting at the center. And to show you what they got, I sliced the beach ball from the top to the bottom and opened it out and spread it out over here. And so what they're seeing is they're seeing some red hot regions and blue cold regions. And they have a way to measure the temperature. And the first thing you can think about is the average temperature across the whole sky. And so you have all the temperatures on each of these little spots, and you can add them up and divide by the number of spots and get the average. And that average is 3 Kelvin, roughly 3 Kelvin. So Kelvin is the scientific scale for temperature. And this room is roughly at 300 and a few Kelvin. So 3 Kelvin is very, very cold. At 0 Kelvin, all motion stops except for quantum mechanical uncertainty principle motion. So this is very cold. But once you've got the average, you might be interested in the bumpiness, the difference between the red hot spots and the blue cold spots. And that bumpiness in the temperature is roughly 30 millionth of a Kelvin. So if you take the ratio of 30 millionth of a Kelvin divided by the average, which is 3, you get 10 to the minus 5, or 1 over 100,000, or 0.001%. That's the bumpiness, the difference between the red spots and the blue spots. They're smooth to 1 part in 10 to the 5. So it doesn't matter whether you're looking here, or you're looking here, or you're looking here. You see roughly 3 Kelvin everywhere. And the difference from those points is 1 part in 10 to the 5. So it's very, very isotropic. This is much more bumpy. So you look over here, you see a cluster. You look over here, you don't see that many bright galaxies. So these are two very, very, very important facts about reality. So one is that in our neighborhood locally near us, up to scales of tens of millions of light years, the distribution is different in different directions. But when you get out to larger scales, over like hundreds of millions of light years or larger, the distribution looks the same no matter what direction you're looking in. And these are very important for cosmology, but I'm not going to talk much about them anymore. If you're interested in following up on this and see how people make sense of this in cosmology, you can go to your favorite search engine and look for the inflation model of the very early universe. And you have to be really careful what you read on the web. I mean, Wikipedia is really good, Scientific American, Discover, Sky and Telescope, but there's a lot of junk out there, so you have to be careful. And inflation is thought to happen when the universe was maybe 10 to the minus 33 seconds old. It's about 13.75 billion years old now. And the predictions inflation makes are consistent with the measurements we have now, but our measurements are not precise enough to test inflation. So most cosmologists think it holds, but it hasn't really been established yet. So those are the two easy things to appreciate. This one is a little bit more difficult to appreciate. And so if we think we have an expanding universe, then we've got to have measuring devices. And I have a measuring device over here that's not expanding in exactly the same way, because if this was expanding the same way the universe was expanding, we'd never know the universe was expanding. So the first thing we need to do is kind of appreciate why this might not be expanding and the universe is expanding. So on the scales of this object and on the scales of the universe, there are two forces that are important, and I can drop this again. That's gravity. And what gravity is, it's described mathematically by Newton's inverse square law. So if you have two masses, they pull on each other, and they pull on each other in proportional to their masses. And there's also Newton's big G in there that tells you the scale of this phenomenon. And the other thing that enters is the distance between these two masses, and that shows up in the bottom of the equation, in the bottom of the formula. It's in the denominator, and it shows up as a second power, so it shows up as distance squared. So if you double the distance, then you get 2 squared in the denominator, and 2 squared is 4, so the force goes down by a factor of 4. If you triple the distance, you get 3 squared, and that's a 9 in the denominator, so the force goes down by a factor of 9. So that's the inverse square law and gravity, and it's an attractive force, so everything gets pulled to everything else because masses attract each other. There's no anti-gravity in that sense. The other force that's really important on these scales is the electric force. And unlike gravity, the electric force has two kinds of charges. There are negative charges, and an example of a negative charge is an electron. And there are positive charges, and an example of a positive charge is a proton. So we have a lot of stuff around us right now, and everything's pretty much made up of atoms or molecules. And atoms have a nucleus, and the protons live in the nucleus along with neutrons. And then very far away, the negative electrons orbit the nucleus of the atom. And the electric charges also obey an inverse square law. It's called Coulomb's law. There's one difference. So like charges repel. So if you bring two electrons near each other, Coulomb's law is going to push them apart. If you bring two protons near each other, Coulomb's law is going to push them apart. And unlike charges attract, so if you bring a proton and electron near each other, Coulomb's law will pull them together. So the electric force has an attractive part and a repulsive part. And that differs from gravity, which is always attractive. So they're both inverse square law forces. So if we take two protons, gravity is going to try to pull them together. And they both have charges, so the electric force is going to try to push them apart. So does anybody have a guess which force is going to win? Is the electric force stronger than the gravitational force? Yes? Okay, so who thinks the gravitational force is stronger than the electric force? 1, 2, 3. Okay, who thinks the electric force is stronger than the gravitational force? 1, 2, 3, 4, 5. And most of you didn't put your hands up, so are you just really shy? Okay, so it's actually the electric force is stronger, and it's stronger by a huge, huge factor. It's 36 powers of 10. So it's very, very, very strong compared to the gravitational force. And the electric force, okay, so let's try a few more questions. You have masses and charges, and you're sitting next to somebody who has masses and charges. So are you repelling the person next to you through the gravitational force? Are you pushing away the person? Do you have a question? No, you're answering it. So who thinks you're pushing your neighbor away through the gravitational force? 1. Who thinks you're pulling your neighbor through the gravitational force? 5, 6. Okay, so you're actually pulling your neighbor gravitationally, but your masses are very, very light. And so you don't notice that pull. But if I scaled up your masses to the masses of planets, you'd pull on each other much more strongly. And if I scaled up your masses to the scale of galaxy masses, you'd pull much more strongly. Did you have a question?
Yeah. Like about the Earth, like if humans make a pole from the North Pole to the South Pole.
Yeah.
If someone jumps in it, what will happen?
They'll start oscillating.
Because gravity is pushing this way and gravity is pushing this way.
Well, gravity is always pulling you, so they'll pull you. You'll go fast as you cross the center. Then you keep going, and then you get pulled back. Be like a yo-yo. Yeah. And okay, so you're also made up of protons and electrons. So who thinks you're pulling your neighbor through the electric force? One. Anybody else thinks you're pulling your neighbor electrically? Two. Who thinks you're pushing your neighbor electrically? Were you answering yes to both? Okay. So I mean, there are certain exceptions, but you're made up of atoms, and atoms have the same number of electrons as they have protons. So if you think about what your electrons are doing to your neighbor's protons, they're pulling your neighbor's protons towards you, but they're pushing your neighbor's electrons away from you. So you're not doing anything because those two forces cancel out because the electrons and protons have the same charge. I mean, there are a couple of exceptions. Did anybody bike in here today? Okay, so maybe you built up some static charge, and then you'd have a charge imbalance, and you could attract your neighbor or repel your neighbor depending on your relative charges. And the other thing you can do is comb your hair pretty vigorously, and you've probably done that with a balloon, right? You scrubbed a balloon on your hair, and then it sticks on you. And that's because you're building up excess charge that way. So you don't have a charge if you haven't biked or you haven't combed your hair vigorously because your electrons and protons balance each other out. And on large scales, there's no excess charge. So this guy is actually held together by the much, much stronger electric force. But as you get to larger and larger scales, there's no excess charge, and the electric force is irrelevant. And even though gravity is much, much weaker, as you're going from humans to planets to galaxies, the masses become stronger. And so gravity always wins on large scales, and the electric force always wins on small scales. So the electric force holds this guy together while gravity makes the universe expand. And that's kind of a difficult thing to appreciate. And so we have to go back and think about gravity a little bit. So Newton had this inverse square law of gravity. And the way he derived that from his observations was that he assumed that there was a fixed space and a uniform time, and that as that apple was falling, space and time didn't respond to that falling apple. And that's what gravity was by the 1650s. And then in the early 1900s, Einstein came along, and he said, if I make space and time dynamical and allow it to respond to that falling apple, I can give you a more accurate picture of gravity on certain length and time scales that look better than Newtonian gravity, better than the inverse square law. And this picture works when things are moving at speeds close to the speed of light, and they work better than Newton's picture of reality. And it works better than Newton's picture of reality when you're in really strong gravitational fields, like in the field of a black hole. And it works better than Newton's picture of gravitational reality when you're thinking about things on very, very large length scales, on scales comparable to the part of the universe we can see. And it's described as by the general theory of relativity, and it makes space and time dynamical and space and time deform as that apple falls. And it's a bunch of mathematical equations. They're partial differential equations that are coupled and nonlinear. And it's very difficult to do anything with these equations unless you've taken enough physics classes. So what I'm going to do is I'm going to solve these equations mathematically and then translate those solutions into English so that I can tell you what they do. And that translation is very inexact. So I'm going to start out in a one-dimensional space. So I have a one-dimensional space here. And so I'm asking you to ignore the width here and just look at the length along here. And I'm going to set up my origin over here. And I can measure along here. And if I give you the distance to this point, you know how far away you are from the origin. If I give you the distance to this point, you know how far you are from the origin. So I just have to give you one number with units. And so that's why it's one-dimensional. And I've got a wave on this space, and I've also got my measuring device over here, which is held together by the electric force. But Einstein's going to come along with general relativity, and he's going to make the universe expand. And you can see what happens to that wavelength. So the wavelength is the distance between peaks or troughs of the wave. And the wavelength gets bigger and bigger and bigger and bigger as the universe expands. And if the universe contracts, the wavelength gets smaller and smaller. So if you start out with blue light that has shorter wavelength, as the universe expands, it slowly turns into red light. And that's the way we figure out the expansion of the universe. And we have our fixed measuring devices that are held together by the electric field, and general relativity is causing this expansion. So there's a number of things wrong with this demonstration. So first of all, in the simplest model that describes reality, there are no ends to the universe, there are no edges. Because if there was an edge, you could walk to it and you could look out, and outside would look different than looking inside. So this is a flat universe. It's a flat one-dimensional universe. I have a flat two-dimensional space here. And you could do the same thing. You walk to the edge and look out, it'll look different than when you look in. So it's not isotropic, and I told you the distribution's isotropic. And the way you make it isotropic, you just take the edges and send them out to infinity, and there are no edges for you to look at. And this expansion doesn't just happen in one dimension. We live in 3 dimensions. There's a vertical axis here and 2 horizontal axes. And the expansion happens isotropically in all dimensions. And nobody's sitting, general relativity is not going to the ends and pulling. What it's doing is it's creating more space in space. And that baby space that it creates grows up and has to go somewhere. And so it starts spreading out, and everything lives in space, and that has to be taken along for the ride as space expands. So that's the expansion of the universe. It's just general relativity creating more space. And this guy first discovered this red shifting from that the blue light turns into red. And he did his observations at on this telescope, which is at Lowell Observatory in Flagstaff, Arizona. So how many of you have gone to Grand Canyon? Anybody gone through Flagstaff? Anybody seen this? You can see this telescope. They'll take you on a tour of it. And if you're Kansan, you might be interested in another telescope there. It was the telescope Tombaugh used to discover Pluto. And Pluto used to be a planet, and I guess in the Kansas Constitution, it's still officially a planet. Just kidding. But, so what he did is he pointed this telescope at objects far away and collected the light and passed that light through diffraction gratings or prisms, broke them up into its spectrum, and compared the wavelength that he was seeing to the wavelength those atoms were creating in the lab, and he found things were redshifting. And the next thing that happened was Hubble came along with a much bigger telescope about 15 years later, and he could actually resolve individual stars in these galaxies that Slipher was looking at. And he found pulsating stars. The ones that he was really interested in are called Cepheids, that's C-E-P-H-E-I-D. And these guys are really useful. So the most famous Cepheid is Polaris, the North Pole star. They pulsate extremely regularly, so they get bigger and smaller, they get bigger and cool off and get dimmer, and then gravity pulls them back in and compresses them and makes them hotter and brighter. And they do this very, very regularly. And these guys are really useful because of a discovery that Henrietta Leavitt had made, I think in 1907. So she had realized that from the pulsation period, from how fast these stars oscillate, she could figure out the wattage of the star, how bright it is intrinsically. She could figure out from the pulsation period whether it was a 100-watt bulb or a 1,000-watt bulb, much, much bigger wattages, but she could tell you the wattage. And once you knew the wattage of that object, you can look at it with your photometer and measure how much light you're getting, and then from the inverse square law for light, you can figure out the distance. So from this relation, which is called Leavitt's law, between the periodicity and the wattage, you can get the distance to the star. And Hubble measured the distance to these stars, and he discovered that Slipher's speeds, the Doppler effect that he was seeing, is linearly related to the distance to that galaxy. So a galaxy twice as far away would move twice as fast. A galaxy 3 times as far away would move 3 times as fast. And you get this linear relation. And you can see that this is satisfied by the measurements. So this is a very famous figure. It's from Wendy Friedman's group from 2001. The final results for the Hubble Space Telescope key project to establish Hubble's law more accurately. And that was one of the reasons the Hubble Space Telescope was built. And the speeds at which the galaxies are moving are on this axis in kilometers a second. So that's 10 to the 4, 20,000, and 30,000. And the distances are on this axis over here. So a galaxy 100 megaparsecs away from us is moving away at about 7,000 kilometers a second. A galaxy 200 megaparsecs away from us is moving away at 14,000 kilometers a second. And this straight solid red line is the Hubble law. The velocity is proportional to the distance. And I'd probably better finish up. So I guess hopefully those of you in the front row have medical insurance. So this is a two-dimensional expanding universe. And my galaxies are well described by Newton's inverse square law. So the galaxies themselves don't expand in size once they're formed. It's the distance between the galaxies that gets bigger and bigger. That's why the galaxies are these stuck-on pieces of paper. So this is a two-dimensional surface. It's got, you can specify a latitude and longitude, and you'll know where you are. And so you're a little ant, and all you can do is walk on the surface. You've got to ignore the outside, and you've got to ignore the inside. And there can be two kinds of ants. So there's the poor ants that can walk, and there's rich ants that have rockets. And you can kind of think about what a rich ant sees. So if you have a rich ant going in a rocket, that rich ant is going to have a Doppler effect. The front and the back are going to be different, and the sides are going to look different. And that rich ant is not going to see an isotropic universe. Only the poor ants who are at rest with respect to the expansion see an isotropic universe. And so they're privileged observers. So if we live on one of these galaxies, and I think I have a denser set of them somewhere over here. They're over on this side, so I'll try to rotate it a little bit. So if we live in this galaxy and look at the light from here, so you have a telescope and you have a diffraction grating, you break up that light into its spectrum. If this guy emits blue light, it's going to take some time for that light to get to you because it has a finite speed. And that light will get redshifted a little bit, and you'll start seeing a purplish tinge. So if you go to a further away galaxy, it takes longer for that light to reach you, and more space is being created, and you'll have a redder tinge. And you go to a further away galaxy, it takes even longer for that light to reach you. So further away galaxies are going to be redder. They're going to be moving faster because there's more space created, and that's what gives you Hubble's law. And I should probably stop here, and I'm happy to answer questions for as long as people want to ask them. Thank you.